In this video, we will discuss potential energy diagram, activation energy, transition state, reaction rate and temperature, reaction rate and catalyst in terms of collision theory. According to collision theory, for a reaction to happen, there must be collision between the reactant molecules. But not all collisions will result in the reaction and giving products. So for a reaction to happen, two things must occur. That means the molecule must collide with the appropriate orientation for a reaction to occur. What does that mean? Let us consider this equation, that is 2NO gives N2 plus O2. For this reaction to occur, suppose we have the orientation like this. Okay, and then oxygen and oxygen and nitrogen in the right orientation. And then we will get the product N2 and O2. But if the orientation of nitrogen and oxygen is like this, no reaction will occur. And the second thing is the molecules must collide with enough kinetic energy to react. What does that means is they must meet or exceed the energy of activation. Or we will say that collision must be effective. So the frequency of these effective collisions determines the rate of that reaction. We can show the energy possessed by the particle as the reaction proceeds by this energy diagram. Molecules with enough energy will reach to the highest energy level here. So notice that in the example reactant here, carbon to nitrogen bond, that's the old bond in the reactant, breaks, and the new bond, that is carbon to carbon bond, is formed in this example. So old bonds are breaking and the new bonds are forming. So how is that happening is the atoms in the molecule are reorganized at this highest energy level. So the organization of the atom at this highest energy state is called the transition state or the activated complex. So the energy needed to form this state, we call that as activation energy and represented by EA. We will discuss two types of reaction and their potential energy diagram. The first one is the reactions that releases energy. They are called exothermic reactions. So that means the system loses heat and the surrounding heats up. So when you measure the temperature, you can see the temperature is going up. And we can plot the potential energy for exothermic reaction as shown in this potential energy diagram. That means we will have reactants with a more potential energy than the product. So for the product, the potential energy at this level, and for the reactant, we can see the potential energy here. So when you see the difference between the potential energy of product and reactant, you can mark that one here. So that will be our enthalpy change, which is going to be a negative value because product minus reactants will give you our delta H value. So products got a lower energy than the reactant, so the delta H value will be negative. Second type of reaction is endothermic reaction. That means it will gain heat and the surroundings will cool down because it is absorbing heat energy from the surrounding. So you can see that the temperature is going down for the surroundings. So for the endothermic reaction, the potential energy diagram will look like this. The difference between the exothermic and endothermic is that you can see the energy of the reactant is less than energy of the product. So here the reactants, and for the product, when you plot it to the y-axis, you can see the energy of the product is higher than energy of the reactant. So when you write the difference between the energy of the product minus energy of the reactant will be a positive value. So that means delta H is going to be greater than 0. So we can mark the delta H, the difference between the energy levels of the reactant and the product. So that will give us the enthalpy change for the endothermic reaction. Now we can go ahead and discuss the different parts of the potential energy diagram. Say for example, what is the potential energy of the reactant, what is the potential energy of the product, how much is the activation energy, and how much is the activated complex energy. Okay, so energy of each one we will go ahead and discuss, and delta H we already discussed, that is nothing but energy of the product minus energy of the reactants. Suppose you have an equation given like this, that is C plus O2 gives CO2 plus 395 kilojoules. What is that means is it is an exothermic reaction. How will you identify an exothermic reaction is by looking at the heat energy. Where is it written? If it is written on the right side of the equation, you see that these are the products here. It is on the right side of the arrow mark. So this is an exothermic reaction. So exothermic reaction, we will add heat energy to the right side. Another way of writing that one is, instead of writing as a product, we can just write C plus O2 gives CO2, and we will write delta H separate. Since it is exothermic, releasing heat energy, we will have a negative value of delta H, and we will write negative 395 kilojoules. Instead of writing as a plus product, we will just write delta H equal. So these are the two ways we can represent an exothermic reaction. How are you going to show that energy change, enthalpy change in the potential energy diagram is, so the reactants are here, carbon plus oxygen, and it is releasing energy, and it is going to form the product CO2 by releasing 395 kilojoules. So the difference between the reactants and the products, we will mark it as 395 kilojoules. So that's how we are going to show in the potential energy diagram for delta H for an exothermic reaction. Now let us see an example for an endothermic reaction. So for the endothermic reaction, here's calcium carbonate, CaCO3 plus heat energy. We can see that heat energy is on the left side of the reactant. So left side of the reactant, we can write either heat, or in specifically if the number is given, we can write that number here. Or we can just write heat, okay, to show that this is an endothermic reaction, and it gives you the product calcium oxide and carbon dioxide. So another way of writing that one is calcium carbonate. We will not show the heat energy or anything on the left side. We will just put an arrow mark, and we will write the products, and then we will write in terms of delta H equals, since it is endothermic, we will just write positive value. You don't have to show the positive value. By default, it will be positive if you are not writing a negative sign there. It is by default, it is positive. So this is another way of showing an endothermic thermochemical equation. Okay. And in this case, we can see that reactants are at a lower energy state and the products are at a higher energy state. So we can get a change in energy 176 kilojoules as per the equation given here. So that's how we can show for the endothermic reaction the difference between the product and the reactants. That energy difference we can label it as 176. So that's an endothermic reaction. And now let us see this potential energy diagram. On the y-axis, you can see 100, 150, 200, 250. The scale is marked like that for the potential energy. And let us see how can we mark the potential energy of the reactant. Where is that reactant on the y-axis? We can see that it is at a 200 kilojoules of potential energy. So we can say that the potential energy of the reactant is 200 kilojoules. And now, what is the potential energy of the product? On the y-axis, we can see that it is at 350. So we can say that products have 350 kilojoules of potential energy. And now, that 150 is the difference between the product minus reactant. So we call that one as what? Delta H. So the difference between the highest peak and the energy of the product is 100 kilojoules. So total, how much is that? 150 plus 100 is our activation energy. You can see that that is 250 kilojoules is our activation energy. So mark the delta H, mark the activation energy, and then we can mark the energy of the activated complex. That is going to be from bottom to the top. That means we can see that it is at 450 kilojoules. And one more thing I want to point out is that the energy of activation for the reverse is, that is from the product to the highest peak. What is that height is, the energy difference is, we can see that 450 minus 350, that's going to be 100. So for the reverse reaction, the activation energy is going to be 100. And for the forward reaction, reactance to the product, reactance to the peak. That means it's going to be, so for the forward reaction, activation energy is going to be 250 kilojoules. And for the reverse reaction, the activation energy is going to be 100 kilojoules. So that should be from products to the peak, and for the forward reactance to the peak. That's the difference. Now let us see what happens when the temperature is increased. As you know, when the temperature is increased, the kinetic energy of the particle increases and the molecule speeds up and collide more frequently with a more energetic collision, right? And now, only those particles represented by the area to the right here, right of the activation energy mark. This is the activation energy because energy is marked on the x-axis and number of particles or fraction of molecule that will take part in the reaction is marked on the y-axis. So we can see that only these particles on the right of this activation energy will react when they collide because that's the minimum energy required for the reaction. Only if that has this minimum energy can react effectively by effective collision, right? So the majority don't have enough energy, so what they will do, and they will simply bounce apart. So for the same amount of gas, if we are increasing the temperature from the lower temperature to higher temperature for the same number of particles in the reactant mixture, what happened? We can see that the more molecules, higher temperature, more molecules are energetic enough to achieve that activation energy. Thus, what happens? More molecules react and the overall reaction rate increases. So we can notice, you can notice that more molecules are to the right now, right of that activation energy now. And what will happen? The reaction rate will increase because we have more effective collision happening at higher temperature. So more molecules will be having that effective collision. So the reaction rate will increase. In the same way, we can explain the effect of catalyst on the reaction rate. So what happens when you add a catalyst in the reaction mixture is, catalyst increases the number of effective collision, and also what it will do, it will provide a reaction pathway which is very lower in activation energy. So in this example, we can see that enzyme is a catalyst. So without enzyme catalyst, the activation energy is here to the reactant energy, whereas with catalyst enzyme, the activation energy is very low from the blue peak here to the energy of the reactant.